Can you hear me now?
Does not work in the OFF position. That's my favorite trouble report.
All right, we're already going to give you a little bit of a sneak preview of what we want to show you. But first off, I'd just like to say thank you for having us. Let's go ahead and get to the first slide.
Sorry about that. Slideshow. Slideshow.
Just go click on that, just go all the way up. Just go. There you go.
You gotta love PowerPoint. There we go. All right. Okay, so go ahead and just go to the next slide, Mark.
Yeah.
So what we'd like to do is we'd like to talk to you, just do quick introductions, who we are, talk about real RFI. And when I say RFI, what do you think I'm talking about? Radio frequency interference. Some of you guys don't deal with it all, I'm sure. And we're going to talk about technology, what's involved with using new techniques to geolocate and then isolate sources of RF interference in your network. And then we can obviously take Q&A and go from there. The one thing that we do want to show you, if it works out, which I think it will, we've got the bandwidth, is an actual live system from the city of Phoenix.
Going backwards.
You're having a hard time with the PowerPoint,
I am.
huh?
I am.
There we go.
Agenda, yes.
All right. So, who are we? Mark, you can tell them a little about yourself.
Mark Rasor, Signal Monitoring Solutions. So like Rob mentioned, we've been doing this for a few years now. So through many different companies, one of the best ways I've found to track down interference in the real world is with TDOA. So we went off and started our own company to do that and focus on that and bring that solution to you as something that can actually work for you. So Signal Monitoring Solutions, small company. Testforce, my partner, Rob, for this purpose, they are providing sales for this product, but they provide a wide range of test equipment for all kinds of land mobile radio and other markets.
Correct, yeah. I used to work for a company called IFR. Any old timers out there? Aeroflex, right? So if you got an IFR, Aeroflex, they're now in Viavi. I ran that business unit for 20 years for them. So yes, it's true. Between Mark and I, we've got 80 years experience. So go ahead.
So we're not pitching a product here, but I am pitching an approach, a technical approach to finding interference using modern tools. So the old way is the boss calls or the fire chief calls and says, I can't get this dadgum radio to work, get out here and fix it. And you jump in your truck with a Yagi and a handheld spectrum analyzer and you start driving around. And guess what? The interference is no longer happening, or you're not anywhere near it, so you can't pick it up. It's a very long and frustrating process. And so what we're going to demonstrate here through a series of stories that I've been personally involved in with our customers in the field is tracking down these bits of RFI. And the first one I want to talk about is Phoenix. So Phoenix, Super Bowl a couple of years ago. When the Super Bowl comes to your town, they bring every three-letter agency you've ever heard of, and maybe a couple you haven't. Everybody's there. They're looking for trouble. They are on high alert. They have a network operations center, a command center set up, and the FBI and the XYZ and everybody else is there. And they're looking for any trouble with traffic lights, with mobs building up, with crime spurts, or certainly when 53% of the public safety radio frequencies go out.
Mark, yeah, let me interject.
Yeah.
So 3 days before the Super Bowl, 2023, true story, 54% of the police radio frequencies in Phoenix all of a sudden went out. okay? So that invoked a response. It's a funny story, right? If you want to learn more, you can talk to us back here afterwards. We've got white papers on it and all that, but it was catastrophic, almost. And Mark's going to go through and show you some technical techniques that he used to quickly isolate the problem.
Yeah, so the hero of the story, we'll call him Brad. He's the guy that's responsible for the radios working. So when the fire chief calls the mayor and the mayor calls somebody to choose somebody out for the dadgum radios not working, it's Brad. So Brad gets all the alarms and alerts. Oh my goodness, this terrible catastrophe. A whole bunch of radio channels are out and they're intermittently coming and going now. What's going on? And so Brad, the hero, is working with me, and we had just installed a network for them there in Phoenix. So I jumped on it remotely and analyzed it, and as you can see in the, hope that's coming through clearly, you can see several spikes there. And the interference, the first thing I noticed looking at it broadband is it was interference on only their frequencies and all of their frequencies. So I'm thinking one of two things. That's an intentional jammer, that's how I'd build it. Or it's yet another one of those doggone BDAs. Of course, that's much more likely, and that was the case. So we analyzed that, zoomed in on it, got some details here. We can see that it's speckles. It's little bits of quick pulses. They turn out to be 8 millisecond pulses. What the heck is that? Doesn't matter. It's on their frequency, and it's causing illegal carrier alarms, taking them out of service. So in the frequency domain, it looks like a jumbled mess, but in the oscilloscope view, it's pretty clear that these are little pulses, all at the same frequency, coming on intermittently. And, oops. So the fun part begins. So Brad, our hero, has me on speakerphone through this whole drama. And I'm sure some of you have done this before. You get all the way down to knocking on the door, and somebody doesn't want to open the door and let you in to investigate the interference they're absolutely causing, right? That's happened before. Well, it helps when the FBI and the FCC and the XYZ and the ABC agency are in town.
Yeah, we're not going to tell you who caused the problem, but it starts with Microsoft, anyway.
So our hero Brad shows up with his FCC buddy in tow and his Department of Homeland Security buddies in tow, and the fire chief and the police chief into the parking lot of this not quite named data center. And they just turned on their BDA and left for the day. So the gate guard is standing there, and he says, excuse me, you stop, you can't come in here. He says, you have to let us in. You're causing interference with public safety radio, and we're from the government. He said, I was especially told not to let anybody from the government in here. In the next 10, 15 minutes, 18 cars showed up in the parking lot, some black unmarked government SUVs, some with blue flashing lights. Just everybody showed up to this party. And finally, this gate guard relented when the magic words were issued. So if you're ever having trouble, the magic words are, son, this was a misdemeanor when you accidentally caused interference. But now that I've told you, you're causing interference. You're purposefully interfering with our public safety radio network. That is now a felony. And I could, through the speakerphone, I swear I could hear the guy reaching behind his back for his handcuffs. And at that point, the poor helpless gate guard threw up his hands, and Brad had somebody go in, turn off the
So yeah, guess what it was? Who wants to take a guess? Misconfigured public safety DAS system, okay? So what Mark didn't tell you, though, is the city of Phoenix actually had 3 teams on rapid response call throughout the city. And when this hit, all 3 teams, 4 people each, jumped out, got their Yagi with their handheld spectrum analyzer, and within 5, 10, 15 days, they probably still wouldn't have found it because they couldn't see it, okay? And what Mark's going to explain, the technology that we're going to talk about, we were able to isolate it in about how long?
Generously, it took a little fiddling, so it was 20 or 30 minutes. It was very low level signal by the time it got up to our towers because the directional antenna was not aimed at any of our towers, any of our receivers at the moment. So it's very low level signal. pulsed and very narrow bandwidth, and only some of the towers were getting a good picture of it. So it took just a little bit of fiddling and turned off some receivers, and then bam, the picture crystallized, and oh, it's coming from this region. So now these multiple teams of highly trained technicians, there's nothing wrong with their equipment or anything, they just couldn't pick it up because it was too low level and there were too many buildings in between them and what they were trying to listen for. So I sent them to the intersection. They got to the intersection, and I thought it would be within a mile or so of there. But in fact, it was at that intersection across the street, and the Yankees at this point clearly picked it up. Bzzz, it's coming from over there. Let's go over to the Microsoft facility and knock on the door.
That was a data center, it was a DAS system, misconfigured, not installed right. As they left, they turned the level from, if it's 0 to 10, what do they turn it to? 11, right? And they leave. And the other thing is the FCC was using a direction finding, a pretty advanced direction finding system. But if you look to the lower right of that slide, what is that? That's pulses. Do direction finding systems work on pulsed RF? Not very well.
Not very well. There is a, there's a highly classified thing called the Beastmaster that some of their high-end teams use. And that is straight up EW stuff that you use on the battlefield. And that handheld unit was able to pick up the pulses and DF on it. But the standard commercial grade FCC teams, their rooftop vehicle DFs, they just can't pick up on that. They're assuming that it's a COM frequency that's open long enough for them to rotate and get a bearing.
All right, let's go ahead and get into TDOA.
Yeah. Okay, so what the heck is TDOA? Time difference of arrival. A transmitter there in the middle of the cloud transmits, and the same signal is received at four or more receivers around there at slightly different times. Same signal arrives at slightly different times, time difference of arrival. So a basic network is four of these. There's a central computer that is getting samples of IQ from all those four receivers, and a local and/or remote user, and that's TDOA. And why use this? Why use this instead of Yankees? Well, because the receivers are up in the towers, and so they've got great commanding views over the whole region. And they've got good antennas and good amplifiers. And so we get a good clean copy of the signal. So this system will get you really close, really fast. We'll demonstrate here in a little bit that we can transmit for 10 seconds and get a really quick bead on where it is. Then you go out there with your Yagi, you know where to go, and you can start and pick it up and knock on the door.
So what we're using, some of the core aspects of this, I can already see some people wondering, how does it know what time it is, right? GPS, that's a critical part of the system. So getting the GPS timing accuracy in conjunction with the trace data, as well as some IQ samples, we can bring them into a centralized processing unit, look at them in relation to time to each other, and then figure out what the difference is. And Mark will go into that a little bit more.
Right. So recurring theme here in story 2. So the hero of this story, again, is the radio guy in Austin. We put in the network that they purchased, and within 20 minutes, we'd found a bad BDA. How? There was a tiny little signal received at one of their tower sites on frequency. So that's a bad thing. We should go find that. They happen to have a crew at that receive site. So they dutifully pulled out their Yagi antenna and their handheld spectrum analyzer and their amplifier, and they went like this, and they saw nothing because they didn't climb the tower, lazy gits. No, had they climbed the tower, they would have been able to pick it up. That's obviously inconvenient. So even though that was an incredibly low-level signal, we were able to get a geolocation on that, sent them to an intersection, and that was right at the Gigafactory. And sure enough, at that point, their Yagis went beep, beep, beep. Oh, right over there. Knocked on the door, shut the problem down. That would have taken, again, weeks to track down. They would have had to drive all over town just to get a whisper of this signal. So, very common. Very common story. TDOA, theory, mathematics, ready? No, this is really easy. Time difference of arrival, imagine two receivers, A and B, draw a line in between them in your mind. Put a little hashtag there at 0 right in the middle. If The transmitter is right there in the middle. The time difference of arrival is 0 nanoseconds. As the transmitter is closer to B by some number, we measure that, and that defines a curve on the Earth. We know now from just 2 receivers that the transmitter is somewhere on that curve on the Earth. That's all. We don't know where it is, but it's on that curve. It's not closer to A, it's definitely closer to B. And sometimes that'll result in higher power at B, but only if your transmitter that you're chasing, the bad guy, is polite enough to use an omnidirectional antenna. Well, he doesn't have to. He can use a directional antenna, and then just because it's closer doesn't mean it'll be a stronger signal at B. So we know he's on a curve there. Add a third receiver, and now you have curves that cross, and where the curves cross, that's where the transmitter is. So it's not terribly different from Rob with a Yagi pointing that way, and me with a Yagi pointing that way, and where the lines intersect, that's where the transmitter is. Very similar, except we do it with omnidirectional antennas. Again, really quick vignette that's starting to sound familiar now. The hero of the story is again, the Las Vegas Metro PD, and put in the system, and I was helping him on the phone this time. And within 10 minutes, we located 2 misbehaving BDAs. One of them was one of their usual suspects, so they ran over and had that turned off pretty quickly. The other one was by the airport somewhere. And so after a few days of using the system, they went and tracked that one down, got that shut down too. And they've been shutting down bad transmitters ever since, as has Phoenix. They've been shutting down 1 or 2 a week. They've just been clearing the weeds out. Potential interferers, maybe not causing a horrible problem today, but trespassers on their spectrum. Get it out of here, clean it up. Shut these things down. How do you hook up such a thing? It's really simple. The blue stuff, that's your equipment. So you already got the antenna, multi-coupler, filters, and
Okay, hold on a minute, Mark.
Yep.
So this is a good point, right? So to make it cost effective, Mark's been doing this for a long time, right? I've been doing it for a long time. This is the first system that I've seen that actually works in the public safety realm at a price that you guys can afford. Now, how do we do that? We're going to take advantage of the filtering and the gains that you get through your RF multi-coupler at your repeater sites, okay? So by doing that, we don't have to have specialized filtering outside of that, especially if you're VHF, UHF band, which can be a kind of a mess, right? But we take advantage of some of that and then tie into that, Mark, the GPS.
right. So TDOA is a general purpose technique. It can be used outside of that. You just take 4 of them out to the desert and make a network somehow, and you can locate transmitters out in the middle of nowhere with a standalone antenna. But for public safety radio, this is the dominant use. So any questions on how it would be hooked up in your system? Okay.
Yeah, we really want to get to the Phoenix demo, so we're going to kind of move through this. But if you have questions, we can talk.
Here's your favorite story, Rob. College Station.
Okay, yeah, this is my favorite one. Okay. So for over a year, College Station, Brazos Valley, they had a problem. And if you guys can see the orange marker there, right? So how many people have a P25 network they're dealing with? Okay, all right. So that is the P25 uplink control channel. What happens when you get interference on your uplink control channel? What do the radios do? They start bonking because you can't get access, okay? So Brazos thought that this was an intermittent interference that was hitting it. So they were just monitoring that. They had their handheld spectrum analyzers, and it would come through for about 3 or 4 minutes, and then it would come back, they'd go away. Everything was fine again. Yeah. So this is not the actual TDOA aspect of it, but it gives you an idea of what doing signal monitoring can do across a bandwidth, right? So what you see here is what we call the Brazos Valley Wanderer. We got a white paper on it. If you'd like it, I'd be more than happy to send it to you. But that system, that particular interferer, if you look at the top, It might be hard to see, but that plateau, which is basically it's a peak hold function, it's like at negative 50 dBm over the air. That's a lot. And it was walking across 450 kilohertz of spectrum. It wasn't intermittent, it was always there. It was just wandering across the spectrum. So they were fighting this for over a year, got into the system, did some geolocation on it. Literally within the first 20 minutes, we were able to identify that it was a wanderer. And then the team was out at 8 o'clock in the morning. By 10 o'clock, they had isolated it to this building in College Station, and it turned out to be this intermod experiment. So, what it was a hard broke on a microwave data link for a public radio broadcast that was supposed to be operating at 945, which it was, and it was doing it perfectly well. But there was an artifact that was 140 megahertz down that was just wandering all over the place. It was a hard broke in the transmitter. Unplugged it, everything went back to normal. Go ahead.
Okay, so how do you arrange a network for this? To get TDOA to work, you have to have a network. So you put 4 or more receivers out there, provide some kind of network. That can be FirstNet on cellular modems, or what works best is using part of your backhaul and allocating 10 megabits per second or so to this, to a computer somewhere, which is often this laptop, or a more substantial server for some customers. And it's really nice to have VPN access into that server. Leave the server at the office, go home, and when the phone rings in the middle of the night, if you're so inclined, you can answer it and log in and get the answer and say, no, Chief, you say there's radio interference. In fact, our spectrum looks clean as a whistle. Let's go check the radios. Or you look at the spectrum and go, yikes. Yeah, okay. Okay, we got a location on that. We'll chase that down first thing in the morning. In the meantime, you're down 5 or 10 channels. But we know what it is, where it's coming from. We'll go get it in the morning.
So for interference, those guys that have chased interference, is it always on? All the time? Is it super convenient for you to go out? No. It's intermittent. It shows up when? 2 a.m. Sunday morning, right? When you're not there, you're not awake. So think about it from this perspective. Okay, this is great, but what if you could go back in time when you get the complaint from the police chief, look at that frequency or number of channels, determine if there was an issue, and if there was an issue, play it back, and then geolocate where it was coming from based on historical data. Okay? Biggest problem you guys have is proving it's there, right? How do I prove it's there? If you don't have spectrum data and you don't have a log file to be able to do that, it's hard to do. This type of a technology gives you the ability to not only look at it geographically using time difference arrival, but log that data into memory for playback. And Mark, a 1 terabyte hard drive will last.
Oh, that's a month's worth, easy.
So you go back
what's
a
a
month.
terabyte between friends these days?
Yeah, a month or two. So, and again, these are new technologies that haven't really been out there. And why can we do this, by the way? It's been the advent of software-defined radios. Who's playing with software-defined radios? Everybody's playing with software-defined radios. There's a lot of software-defined radios out there, but it's really been only recently where we've got good software-defined radios. When I say good, test and measurement quality software-defined radios that allows us to get the timing accuracy, level accuracy that we need to be able to actually do this kind of geolocation. Go ahead.
Yeah. So how many receivers do you need to pull this trick off? Mathematically, 3. Anybody that suggests you field 3 units hasn't spent enough time in the field chasing these things. 3 tends to give you blind spots at the extension of the triangle beyond. If your transmitter happens to be on those lines, you're going to get wacko results. It's just mathematics doesn't work out. The little bit of noise in the system that's causing small fluctuations causes huge fluctuations in the location. 4. 4 is the answer. Put out 4 roughly in a square. It doesn't have to be a perfect square, but make it square-ish, trapezoid, whatever. Don't put 4 in a line. That'll work unless the transmitter happens to be in the line, along that line, then it's a mess. But put 4 out there, try to surround your problem area as much as you can, and it'll work inside that area and a bit outside. We'll show you what happens when it's way outside later.
So somebody's probably thinking, how
Question.
much range?
Yeah,
Oh, go
Rob,
ahead,
that's a
sorry.
good question.
We're going to show you, that's a great question.
Yeah,
So the 2 questions we're going to ask with the City of Phoenix demo, so stick around, is what kind of range does this thing have? How many receivers do you have to have, and how far apart can they be? But also, what happens in a challenging geographical, topographical type of or a situation?
yeah. The real answer is line of sight. Trees don't seem to cause us a tremendous amount of problem. I know in the East Coast, when the foliage is in, that will, if you're trying to pick up the radio through the trees, through the foliage, that actually slows down the speed of light. Radio waves travel slower through a forest than they do across the top of the forest. But as long as that distance is relatively short until it heads up to a mountaintop, that's good. But no matter how much you spend on a receiver, it's not going to see through a mountain. So that's why Phoenix had to add some more receivers to fill in some valleys on the other side of mountains that they just couldn't see through. But
They had the same challenges that we have here.
You get 3 or 4, put them up on the mountaintops such that when the bad guy transmits, he can see 3 or 4 or more receivers up on the peaks with reasonably close to line of sight, then that'll work.
Yeah, we'll show you. Yeah, let's move ahead, because I really want to get to the Phoenix demo.
Sure. Very quickly, Harris County example, got there, set up the network, and the hero of the story said, hey, we've got channels going in and out. A whole bunch of channels are flickering. They're coming up, they're going down. Looked at the geo on the map, and there were dots all over the map. I thought, that's not turning out to be a good demo. What's going on? What was going on is there were transmitters all over the map. So there was a preponderance of dots up at this one area. So most of the transmissions seemed to be coming from there. We drove up there, and it was a piece of misconfigured test equipment. They'd left it in a test mode. And it was transmitting from there, saying, Station 1, are you there? Yeah, good. Station 2, are you there? And so, yes, for several milliseconds at a time, all the stations were transmitting and flickering on and off. But we were able to pretty quickly find that and track it down. And again, turn that off, and whoosh, it all went quiet. What do you look for in a system? It should be really easy to use. The math underneath is straightforward but hard to implement to really get it fine-tuned right. But it's easy to use. Put in a frequency, you get some dots on a map. Off you go. We did not invent TDOA. TDOA has been around and used for decades in multi-million-dollar classified systems for the military, for the intel community. Radio astronomy uses this. This is how we know where the spacecraft are in deep space. This is how we know where the pulsars and quasars are. Sonar really is using the same technology, just at a lower frequency with sound. And GPS kind of works this way, but in reverse. You don't know where your receiver is, but you know where all those transmitters are. It's kind of the same. So my point is, the way to chase down interference today is a combination of TDOA, get to the area really quickly, or maybe watch it for a few days and see when does it come on. Oh, it comes on about 2 p.m., about 2 p.m. to 3 p.m. every day, and it kind of comes from over here. Well, now you send your technician, instead of driving around aimlessly, you send them there at 1:30 and say, wait for it to come up, and then Yagi it down. So TDOA gets you really close, still need the Yagi in the handheld to go across the rooftop, across the intermod experiment, literally, and they went, is it this antenna? No. Is it this antenna? No. This antenna element right here. So you still need that handheld. That's definitely part of the solution. What if the transmitter is very far away. I said put 4, try to surround your area. But you can see here the four blue dots, 5 blue dots, that's where the receivers were, and the transmitter was far away. Well, you just turned your town into a direction-finding antenna array doing correlative interferometry. Congratulations, you have a giant DF antenna array. If you shrink that down, you can put it on the rooftop of your car and drive around. But now you know the direction that the bad transmission is coming from. You just don't know how far away. But you know it's not coming from you. It's not coming from your town. It's them over there.
Okay, one of the things that we're seeing is a rise in intentional jamming. Has anybody run into an intentional jammer out here? Somebody that's either bought something off of Amazon and configured their own. So what's happening is in the bigger cities, LA, the criminal gangs are actually getting sophisticated enough where they're actually building these kind of transmitters that come in and blank out not only Wi-Fi and cellular, but police frequencies, all right? So what does that mean? Going into the future, right, systems that isolate or identify intentional RF interference have to be fast. They can't be hour-long, day-long, month-long chases of interference, right? So this is just something that we're starting to see, and it's not, unfortunately, it's not going to get any better. All right.
Okay. Rob's going to distract you for a second while I get this.
Any questions while Mark's switching over? Okay,
Yeah.
I'll tell you what we're going to do here is Mark, so the city of Phoenix was really kind of a test platform for us. We started dealing with them about 4 years ago, Mark. Mm-hmm. And they had tried a lot of different things. They had tried stuff that was embryonic, stuff that was supposedly proven, and couldn't get anything to work, right? So we spent a lot of time with them. And what we ended up with, they helped a lot with the development. Like I said, this is relatively new technology, right? They helped a lot with the development to the point that they're so happy with Mark and what Mark's been able to do is they give Mark remote access to their secure network. So what you're seeing here is basically it's a redirect of a computer that's on the City of Phoenix network. It's locked down, we're not able to get any data or anything like that. All we're doing is we're just controlling that computer remotely. Right. So what you're seeing is a computer in Phoenix shot over the internet to here.
Yeah.
Okay.
So there might be
But
a
this
little
is
bit
the real system they're using.
Yeah, there might be a little bit of sluggishness because of that. This is most of their network, the blue dots, the receivers.
I'm going to step down here so I can kind of point things out.
Sure. They're actually using a couple of the other receivers. But that's about 45 miles between the farthest set of receivers. So I'm going to turn off some of these for this demo and release these receivers so that they can get back to using them.
Okay, so what we did is we started with 4 receivers, right? Proved the process, it worked. Phoenix, for the last 3 years, has been adding on to the point now that they've got, what do they got, 13, Mark?
Yeah.
And they're adding another 6, okay? So that's the other thing. These things, it has to work, has to be proven to work, but as RF interference issues get worse, which they will, right, you have to have the ability to scale. And that's what systems like this can do for you.
Okay. And of course, the network decided to take a hiccup here, so give us just a moment while we get this reset.
So over here, where you see WTAZ, that's White Tanks Mountain. And then over at TMPK, losing my voice, that's Thompson's Peak. That's how long, Mark?
About 45 miles.
45 miles. Get some feedback here. So if you look at this, you've got a radius of about 20 to 25 miles around that system. And they've got North Mountain in there. You see North Mountain, South Mountain. They got City of Phoenix with high-rise glass reflections, mirror reflections. So kind of what you're dealing with here in Colorado.
Well, I may jump to the end of this while this syncs up, and let's see what it looks like after we play back recorded from stuff we did a little bit earlier today. So we can, there's a database involved, so.
So earlier, we were back in one of the conference rooms, we logged in, and we actually, remember I told you about going back in time? So we actually recorded the spectrum. So we'll show you what we got here.
Right, and in fact, what we did here is we set up several bands for collection. There are about 12 of them. And we said, these are the problem frequencies that have been coming and going. So we've got a problem on these 12 frequencies, and set it to loop through those. Every 2-point-something seconds, it would loop through that whole list of frequencies and look for a problem coming up. Now, we don't need to see all of these. We only want to see those on this RFI shop, and we only want to see it when the peak power is, come on, click, greater than minus 130 or so. I was typing, hello? Click, sorry, network lag going on here, minus 130.
Now, you're getting to see kind of a
greater.
deep dive into the technology behind this. This is not what you're typically going to be using, right? But what we can do, it just shows you where it was coming from, what band we're dealing with, what site location, what frequency, did we capture something, was it a high confidence capture or not? And the software takes care of all that for you, but if you want to get into that level of detail, you can. You can get right into it.
And so what I'm doing here, very slowly over this network that was working really well just before the talk, is I'm clicking through this list, apply, and we'll display these dots on a map. I've filtered it down to just that one frequency of interest, where peak power is greater than X. And if the network will allow, we should soon see dots. Well, this is really fun.
Oh, you saved it on their network.
Yes.
Ah, okay, got it.
All right. That's a bit speckled, so hang on a second. Let's clear that map. It's dealing with my last 5 requests over the VPN. Clear. Well, I want to see when confidence is greater than equal to 100. 100. Apply. And I'm trying to filter this down.
So what we're doing is we're taking a lot of different measurements. You're seeing the dots starting to pop up on the map, and what the system is doing right now is it's refining it, basically saying, how do we get down to what is usable information, right? Mark, we got about 5 minutes.
Yeah, I apologize. The network lag here is, I've clicked on
It was
about
working great
10
earlier.
things, and it's trying to work on those last 10 things, and it's just
You want to see if you can go live?
Yeah, let's do that.
And if not, come back and talk to me. We'd be more than willing to do this. We've got systems all over the U.S. right now. Like I said, it's still fairly new, but we got them in major places. We got them in Phoenix. We've got them in Las Vegas, Austin, Houston, North Carolina, Viper, Kansas City, LA Ricks. So if you want a demo, let me know. We'd be more than happy to set it up for you.
Map config. All right, one more time. I think we're ready for live. There's the map open. I'm going to pause collection. I'm going to clear the map. Clear. Okay, here it comes, I swear.
All right, so what you're going to see is an actual live interferer. How do we know it's live? Because they gave us a frequency, a demo frequency. So we actually hooked up. This is a signal hound generator, putting out about what? A watt, 2 watts?
Yeah, maybe 2 watts.
On a particular frequency.
And so now we get to commit the sin of RF interference. We're going to jam the heck out of this channel on. Oh, there it is. And look, there are the dots.
See that?
And it's on for a few seconds, coming in at different power levels at the 4 different
We got
receivers.
spectrum data.
Off, it's gone. The
Okay,
signal
now all of a
was
sudden
gone,
the RF goes off.
but we can still see it. So
Right.
I'm going to hit
Wait.
pause.
Mark, hold on. What did you guys just see there? You guys realize what you just saw? You see how, literally within 10 seconds, he had a location. Okay? This is where things are going in the future. In order to be able to respond to RF interference events, you have to have a system that's quick, it's fast, right? Especially when you start dealing with intentional jamming, because it can cost a police officer their life. It really could.
Yeah. So here's the time machine aspect. We go back in time to when it was 100%. Okay, signal is down, signal is up. There's the signal. We can see that's really a signal. It's the same signal received at different sites. And we zoom in and we get a tight little cluster of dots. And I happen to know that the transmitter is in fact right here on this building. And like Rob mentioned, that's because I put it there.
So that's the City of Phoenix radio shop right there.
So you take this center of this cluster of dots, say over here, and measure to where we know the transmitter is. Oh, 0.47 miles off. Sometimes it's 0.47 miles the other way. Sometimes it's within a quarter mile.
It's RF.
I did a demo once and put all the dots on the top of the map, and Rob started jumping up and down. I said, no.
That was an anomaly.
The dots are on top of the building. It doesn't always work that well. It's really good, but it's not that well. But it does work better with higher power transmitters. It works better on broader band transmitters.
So think
the
wide
jammers,
band.
the bad boys with the jammers that come
The
into
wide
town.
band stuff is
Wide
easier to
band,
find.
we will put that on with much greater accuracy and confidence. As it gets more and more narrow, 6.25 kilohertz, that's getting to be a little challenging. That's why the dots are a little bit scattered. You take it down to CW with 0 modulation, guess what? There is no time difference between the different stations because it's unmodulated. It's a continuous wave, and it just flat out doesn't work. So if a CW comes up for a couple hours, you got to take your Yagi out and find it. TDOA just doesn't work on that. Modulation, even up to 2 kilohertz, as low as 2 kilohertz, and we'll be able to find it. Somebody's on with a voice transmitter. When they're quiet, analog modulation, you might not get a location, but when they key up and yell into it, sing or whistle or play music or whatever they're doing to cause you a problem, then you can get a location on it.
All right, Mark, we need to wrap up. So
Absolutely.
thank you for your time. I appreciate it. One other question you might ask is how does that interface with my existing illegal carrier alarms that I've got in my system? There is a way that can be done. So with that, thank you very much.
Thanks.
Okay, with that, we are coming to our final presentation of the day.